my screen? Okay, I think my screen is visible to everyone.
Yes, sir.
Yes.
Okay, fine. So let us have a quick revision for the types of shift. So the first type of shift was logical shift, wherein we insert 0 onto either side. If it is logical shift left, then we insert 0 onto the right hand side. So this is the logical shift left. If it is logical shift right, then we insert 0 onto the leftmost side. So there was a loss of information over here. So there was a loss of information, that is 1 bit loss we were having in case of logical shift. But if we discuss about the second type of shift, that is circular shift, wherein what we do is in circular shift left, we perform logical shift by default. But the thing was, instead of inserting 0, we insert the leftmost bit onto the rightmost side. Leftmost bit onto the rightmost side in circular shift left. And in case of circular shift right, the same thing we do, but in the opposite direction. So logical shift right we have performed by default, but from this rightmost bit we are shifting it to the rightmost side. So this is circular shift right. But still, if I move further, the third type of shift which we discussed, was arithmetic shift, wherein arithmetic shift left is nothing but exactly similar to our logical shift left. But actual problem what we understood was, actually it was not the problem, but actually we said it is multiplied by 2. If we shift any of the bit onto the left hand side, we are performing actually multiplication by 2. And if we perform arithmetic shift right, we are performing division by 2. And again in this case, the sign bit, now this is actually termed as sign bit. If it is 1, that means it is a negative number. If it is 0, then it is a positive number. That's why it is applicable to signed numbers. Arithmetic shift is always applicable to the signed numbers. Signed numbers means, in case of C language, we are having two types of integers, signed integer and unsigned integer. So over here we are talking of signed integers. Now, in case of signed integers, if we talk, then in that case, this is your sign bit. If it is 1, that means it is negative number. If it is 0, that means the number is positive. And in this case, if we check, then it is nothing but division by 2. So this is the other type of shift. Just a minute. Yeah, sorry for the interruption. Okay. So the thing is, this is the third type of shift which is applicable for signed binary numbers only. Fine. So in this case, the sign bit we always keep it as it is in case of arithmetic shift right. Whatever is the sign bit, the same is to be copied over here. Fine. Just a minute. Yes, once again, sorry for the interruption. Okay. So over here, so in case of arithmetic shift, arithmetic shift right, always remember this sign bit is to be maintained. So over here it is 1, so it should be 1. Over here it is 0, then it should be 0. Now application of arithmetic shift right will come across into our later chapters. There is one chapter where we require this arithmetic shift right. Fine. In performing some certain arithmetic operations, we require this operation. I will understand at that time again. Fine. Now we are supposed to design the circuit for this. Now we are supposed to design the circuit for the shift operation. But before designing to this circuit, what I want to teach you is, for designing this circuit, we require shifter. So we want to shift the bits. That means we require multiplexer. And over here, I will be considering in general shifter circuit, and that shifter circuit will be only of two types, that is either it will perform shift left or it will perform shift right based on the selection we do for the multiplexer. Now multiplexer is of type 2 cross 1, that means two input, one output. Performing shift right or whether we are performing shift left. If 0 then shift right, if 1 then shift left. Now if it is logical shift then we insert 0, and if it is circular shift then we insert the corresponding rightmost to leftmost or leftmost to rightmost bit into the respective operation. Fine. So these are the outputs. Now understand how this circuit connections we are doing. You will not understand. See, that's why I had put this table in front of you earlier part. See, in this case, actually, let me tell you, say for example, this is my input A0. Sorry, just a minute. Let me again try to change it. Okay, so actual input is A0, A1, A2, and A3. Now just understand. Am I audible now?
Yes, sir.
Yes.
Okay. Now just understand, if I want to perform shift right, I want to perform shift right. That means this A0 should be shifted to this bit position. This A1 should be shifted to this position. This A2 should be shifted to this position. Are you clear with this? Shift right. Okay, but this is the shift done. But what about this position in shift right? What should come over here? If it is logical shift, then this value should be 0, and if it is a circular shift, then this value should be A3. Is it fine? But that's why in general we are writing it to be the value IR. Either it may be 0 or it may be A3. That's why we are saying that it is a serial input. So see this IR. Now you tell me, this IR I have given onto the line 0 of MUX 1. Then what should be on the line 0 of MUX 2? You tell me. Can anybody try? I have already highlighted. On MUX 1, line 0 is given to be IR. So this was our IR. Then on MUX 1, what it should be? It will
A0.
be A0.
A0.
A0. Is it fine?
Yes, sir.
Yes.
What about MUX 2? What should be there on, sorry, what should be there on MUX?
A1.
A1, A1.
A1.
Perfectly. See this A1. See A1 connected. And what about MUX 4? Line 0.
A3.
A2.
A. Is it
2.
fine? Did we get A2? Fine with this? But
Yes, sir.
again moving back, let me discard this numbers and everything. Discard. Moving again back. Okay, now I am performing, say for example, I am having the same bits over here, A0, A1, A, A2 and A3. Now I want to perform shift left. Then can I say this A1 comes over here? This is my A2, this is my A3. Then what should come over
Yes.
here? IL. Okay, so just again tell me. So this was about shift left, but now I am giving shift left. This was for shift right, line 0, but for shift left we are having line 1. So what should be there on line 1 of MUX 1? A1. So see, I have connected A1. Can you see this? What should be there
Yes.
on line 1 of MUX 2? A2. So this is my A2, if you can see. What should be there on MUX 3 line 1? A3. Yes or no?
Yes.
Yes, yes.
This is my A3. Did you get this?
Okay.
And what
Yes.
about H line MUX line 1?
I
MUX 4.
I L.
IL. Did you get this now? So
Yes.
this is what is actual circuit. This is what is actual circuit of shifter. This is also termed as 4-bit combinational shifter circuit. Is it fine? Now
Okay.
see this. I had taken an example. If I give 1001, A01, A11, A01, sorry, A20 and A31. A01, A11, A20, and A31. And I am giving 0 over here. That means it should perform shift right. Shift right means this 1 should be shifted onto right side. See the shifting taking place. Is it fine? And over here, I am writing 0. Is it fine or not?
Yes.
Okay. So this is what is a shift.
Single sir.
Yes, yes, yes.
Single time ही shift होगा ना?
One time. Obviously, it will be one time shift
Okay.
only. Okay.
Okay.
So should I move further? Now, yes, as you
Yes sir.
again, I want to ask one thing to you. मुझे अगर 2 बार करना होगा तो अगर the same thing I want to repeat it again, then if I want to do it twice, then yes, I think who was on the line for asking the question?
Me. Dinesh Triplani.
Yes. Now just answer me how it can be done. Acha, now you only think if I give this output H0, H1, H2, H3, ये जो मुझे output आया है, if I connect it again back to this circuit, then I can get
Yes.
second time, which we'll never
Yes.
do, we'll never do, but I can get the second time, no?
Yes.
Now you should be, all of you, now I'm talking to everyone, you should check out bitwise operators. Our bitwise operators in C language, wherein we are having two types of operators, shift left and shift right. Now you will be very much clear about those operators. But in that case, you are having flexibility, how many times you want to shift. One time, two time, that you need to provide. Fine. So
Okay.
these are the same bitwise operators in case of hardware circuits. So if you are doing in C language bitwise operators, if you apply it, actually at the hardware level, this is happening. Are you getting this?
Okay.
That there will be a mux
Yes.
arrangement wherein this data would be fed and corresponding shifting takes place and you get the output onto your display. So internally, this is happening. So that's why this is the reason why we are studying the computer organization as a hardware subject, because the softwares we are working, we should always know how they are working onto the hardware side. So that is the actual work of engineers. So that's why we are learning the subject of COA. Now, did you get this? Why we are learning COA?
Yes sir.
Okay. So fine, let's move further. See, now we are on the verge of designing arithmetic and logic unit. See, total 3 operations we studied: arithmetic micro operations, second we studied logic micro operations, and third we studied shift micro operations. So now we are going to design arithmetic logic shift unit. Did you get this?
Yes.
Okay.
Okay, let's see the circuit of it. You are already knowing it, huh? I'm not going into the detail of the stories, which you can read it out. What it is written? One stage of arithmetic circuit, one stage of logic circuit. Arithmetic logic shift unit. Just recall our arithmetic circuit. Do I need to recall it? Okay, let me recall that part. See, this is the circuit. Yes. This is the circuit. Is it fine?
Yes, sir.
Yes.
This you need to take it one unit, one part. One part means talking of single bit. This part only. This part. Are you getting this? Okay, let me highlight it.
Yes.
Only one part of arithmetic circuit. That means this one part, not 4-bit.
Okay.
Okay, one part of arithmetic circuit. Then what we require is one part of logic circuit. Okay, coming to logic circuit. So this one part of logic circuit. Again, this is one only. This is single part. That's why I written AIBI. So one part of this. That
Yes.
means only one part. So we got one part of arithmetic, one part logic. We need to combine them. Okay. So let's see to that. Okay. Let me shift it to directly that part. So one part of arithmetic circuit, one part of logic circuit. And how many types of shift we are having? Actually, two types: shift left, shift right. So see this. I had taken one multiplexer, 4x1 multiplexer, wherein on 0th line, just a minute, wherein on 0th line, I have connected one part of arithmetic circuit. On the first line of multiplexer 4x1, I have connected logic circuit part. And on line 2 and 3, I am connecting shift part. On line 2, shift right. On line 3, shift left. Did you get this? And
Yes, sir.
two select lines I require for this S0, S1. So I had given two select lines, S3, S2. I had given the name. Again, I require select lines. So this is my output. Again, I require select lines for this arithmetic circuit also. So carry out two select lines, S1 and S0 for both. Because over here we were using 4x1 mux in this case. Again, in this case, 4x1 was used. So same select lines we are giving to this. Did you get this now?
Yes.
Okay. This is your actual arithmetic logic shift unit. Now what you have to visualize over here is, in the case of arithmetic circuit, one stage of arithmetic circuit, what you are supposed to do is you are supposed to consider that circuit which I had shown you right now earlier, the one complete highlighted part. So that comes over here, and the logic circuit comes over here. Is it fine? So detailing comes over here. So that's why we had just mentioned a block for that. Okay, now just tell me how this circuit will work. Can anybody try? This is my input, huh? AIBI. So one part. That's why we had given one part, AIBI. Okay. Now, can someone try to explain me the working of this circuit? Who can try? Someone from your side.
Sir, this lines, if we put 0, 0, then 0th line will be selected, and same
Yes.
for the
Yes, Mukund. Okay, fine. We'll go step by step, Mukund. Okay. Say for example, for S3 and S2 first. For these two inputs, S3 and S2, say for example, I give 0, 0. Do you agree?
Yes.
What
Yes.
will happen?
arithmetic circuit will be selected.
Just understand what will happen. 0 0, that means over here 0 0 will be there for this multiplexer. And if I give 0 0, which line will be selected?
0.
0. What is there on 0th line? What is there on 0th line?
Arithmetic circuit.
So on 0th line we are having the output of arithmetic circuit. So can I say now, if I give 0 0, then I will be having the output of arithmetic circuit?
Yes.
Now see, I have not mentioned over here which arithmetic operation, but one thing is clear, that means it will be arithmetic output. But what if I give
Yes.
S3 to be 0 and S2 to be 1?
Logic unit.
Can I say over here 0 1? That means line 1 will be selected and we will be getting the output of logic unit.
Yes.
Yes or no? That means, can I say my select lines, if I give 0 1, that means I will be getting the output of logic operation and not any kind of arithmetic operation.
Yes.
Same way, if I give 1 0, then
And then second shift right operation will be.
so what will happen? I would be getting shift right operation. Did you get this? And if I give
Yes.
1 1, then line 3 will be selected.
left.
It will be shift left operation. So can I say now my arithmetic, logic, shift unit is ready?
Yes.
But still I am not clear that if I select 0 0, then it is going to perform arithmetic operation. But which operation? Addition, subtraction, increment, decrement, or add with borrow, or sorry, add with carry, subtract with borrow, or transfer? Which is going to happen? We were having 8 operations now earlier.
Yes.
Which will happen? Now that which operation is going to happen, that will be decided by S1 and S0. Are you clear with this?
Yes.
Same way for logical operations, we are having 16 logic operations. So which 6 out of 16, which logic operation is going to occur, that will be again decided by this select lines. Did you get this? Whether it is going to perform AND
Yes.
or not, whichever going to happen, that will be decided based on this. Is it fine?
Yes.
And regarding shift right and shift left, that we are having direct operations, so we did not to care about that. Okay, now I am going to the truth table of this circuit. Just check out how many inputs were there, select lines were there, S3, S2, S1, S0. Now what S3 and S2 decides? Can I say S3 and S2 decides the arithmetic operation or logic operation or shift right or shift left? Out of these 4, what is going to happen? Okay,
Yes.
so if I give 0 0, if I give 0 0, that means it is surely going to perform arithmetic operation. Yes or no?
Yes. Yes.
Now out of 8 arithmetic operation, which it is going to perform will be decided based on
Transfer.
S1 and S0. So over here we have defined it to be transfer. But let me go to the earlier table. Just a minute. Let me go to the our earlier arithmetic table. The same circuit is applied. See, what is the first operation over here? Which is the first operation for S1, S0?
Add.
Add, yes or
Add.
no? But over here we got transfer.
Yes.
You just check out. Just keep in mind this add 8 operations. Add with carry, subtract with borrow, subtract, transfer a, increment, decrement, transfer. So these are the 8 operations. So just check out. We need to check whether all these 8 operations are covered or not. I'll come to that point. You are in confusion, I know. See this now. See, transfer A, increment A, addition with carry, subtraction with borrow, subtraction, then decrement, and lastly Sorry, increment is there? Yes. So 8 operations are there. Transfer A was 2 times, but I have included over here 1 time. Yes or no? But sir, what about the sequence? In earlier case, there was firstly was add, then add with carry, then subtract with borrow, then subtract, then transfer, then increment, then decrement, then again transfer. But over here you have changed the sequence. Sir, what if we follow that previous sequence? No issue with that. Don't worry, you can follow that table also. Actually, it is the same table. Actually, it is the same table, just 2 columns are added. Which are those 2 columns? S3 and S2. Rest this table is same as our previous table. Is it fine? Let's move further. See this. Now logic operations. See, actually I'd see transfer A, 8 operations we got. Then logic 4, AND, OR, XOR and complement. Then shift right and then shift left. But in case of shift right and shift left, we don't care for S1 and S0 or C in. So that's why I had written don't care condition. Did you get the application of don't care? See, you had studied don't care in reducing the K-maps. Reducing Boolean function using K-maps. You were using don't care. Now this is the real-time application of don't care. See, in case of our circuit, you can check out. See this. For doing shift right and shift left. For doing shift right and shift left, do we care for S1 and S0? No.
No.
Do we care for C in? No. That's why we are mentioning
No.
we don't care. Is it clear?
Okay. Yes, sir.
So this is your arithmetic logic shift unit. Clear with this? With this, your chapter is over. Unit 1 is over. Any doubts with this?
No, sir.
Let's go through some exercise. Can you read the first exercise? Design 4-bit combinational decrementer using 4 full adder circuits. Already we have done. Yes or no?
Yes.
Yes, sir.
I'm asking to everyone, only one student is replying to me. Yes or no?
Yes,
Yes,
sir.
sir.
Ah,
Yes, sir.
see the yes, jo jayega, bada jayega. Now see the next exercise. Design a digital circuit that performs the 4 logic operations of exclusive OR, exclusive NOR, and NAND. Can you tell me how it can be done? Someone who can tell me? Is anyone out there who can tell me? अरे क्यों सब शांत हो गए? It simple exercise है. Okay. Let me. Which are the 4 operations? Exclusive OR, exclusive NOR, and NAND. Yes or no? Already you are knowing this exercise, but you don't want to try. What is this? What you have done over here? ये क्या है आपका? What is this operation? And. Instead of which operation you are supposed to do? Instead of AND gate, you need to take exclusive OR gate. What is this operation?
Or.
Instead of OR, you are supposed to take exclusive NOR operation. What is this operation?
Exclusive. XOR.
XOR. We have already implemented. But over here, which operation you need to take now? NAND gate, you need to take NAND gate. And on 4, instead of NOT gate, what operation you need to perform?
NAND.
NAND.
Not.
So XOR, XNOR, NOR, and NAND. Done. So this is your circuit. Now can't you design this? Yes or no? It's simple, no? Should I move further? Okay, so let's move further with the exercise. Sorry. Yes. The next exercise, just understand, huh? Register A holds 8-bit binary number. So register A contains this number. Determine the B operand and logic micro operation to be performed in order to change the value in A to this. क्या बोल रहे हैं? What they are saying that in register A we are having this bits. In register A we are having this bits. Okay. Now in output I want this bit. Then what operation I will perform so that I can get this particular output? So I am supposed to determine a B operand and logic micro operation. Are you getting this exercise? See,
Yes, sir.
let me still clarify it. What is given in register A? 11011001. Okay, and what I want as an output, what I get as an output is 0
0 double 1 0 double 1.
0 1 1 0 1. So this is my output is. Okay, let me come to the slide, just a minute. Uh, 8-bit, no. Okay. See, in this slide, say for example, what they are saying is in register A I am having 1, then 1, then 0, then again 1, then 1 0 0 1. Sorry, 1. Let me take this into some new slide. Copy in. So this is there in register A. Did you get this? What output they want? What output they want? Let me take it again. Copy. This is the output they want. Let me write the output. The output is 0, 1, 1, 0, 1, 1, 0, and 1.
1.
Okay, fine. So this is the output. So what micro operation I am supposed to perform and what should I set in register B? You get this? This is my
OR operation.
exercises B. So now tell me what I am supposed to do. See, 1 as it is, 0 as it is. Over here I want 1. Over here 1 as it is. Then over here 0. Over here 1. Over here 1 as it is. Over here 0. So what I am supposed to do?
XOR.
XOR. Are you sure? Are you getting my point? what operation I am supposed to do so that I can get this output.
सेकंड वैल्यू क्या लेनी ना उसमें कंफ्यूजन है
Yes, in register B, you can take any value that you want to set accordingly, but you need to get this value. Okay, you just think whether you are going to apply
X.
selective set, whether you are going to apply selective clear, whether you are going to apply selective complement, whether you are going to apply insert, whether you are going to do masking, just think accordingly. This is my input and this is what my output is. ये मुझे output चाहिए. I want this output. Which operation I should apply and what should I set in my register B? That is the question.
XOR
How XOR?
वैल्यू हम कुछ भी सेट कर सकते हैं ना
हाँ अच्छा चलो ये बताओ B हम क्या सेट करेंगे. चलो मैं B कॉपी कर लेता हूँ अभी. Sorry, I copy B. Okay, fine. Okay, चलो अभी हम क्या वैल्यू सेट करेंगे B में. मैं चलो सभी 0 कर देता हूँ. चलो मैं ये निकाल देता हूँ. You just tell me what I should set now.
1
Okay. Okay, who wants to try? Tell me now. What values I should set?
1
Over here?
from starting
From starting, okay, from left. What I should set over here?
yes
1 or 0? Hello?
1 1
1, okay. Then?
0
Okay, then?
0
Then?
0
Then?
हाँ एक मैं वहाँ पे 1 1 सॉरी
Okay, 1. Okay, then?
हाँ 0
Oh, 0? Okay, 0.
0 ही है ना
0. Then?
1
1. Then?
0
Then?
0
Okay. So which micro operation?
XOR
XOR. Fine. Now, just think other way around. Can I apply selective complement?
yes
How? How can we apply selective complement? What is the rule for selective complement? Where there are ones in B, corresponding A gets complemented. Yes or no?
yes
So over here, 0, 1. So this should remain as it is.
yes
0 should become 1 over here. That means I need to set 1.
yes
Okay, this 1 is to be kept as it is.
yes
Okay, now what about this? 1 should become 0. Yes or no?
yes
This 0 should become 1. That means I need to set this value to be 1.
okay
Again, this 1 is to be kept as it is. And again, this 1 should become 0. Now just check it out. Can I say the same thing we have implemented for selective complement also?
yes
Clear, everyone? So the same thing can be adjusted accordingly. So the exercise what I had mentioned over here is that which I mentioned is determine the operand in B and the logic micro operation to be performed in order to change the value in A. The same thing is to be applied for this. If I want this output, then which operation you would be applying? Okay. And the last exercise. See the last exercise. Starting from initial value of R, that means say for example in register I am having this data. Determine the sequence of binary values in R after a logical shift left, followed by circular shift right, followed by logical shift right, and a circular shift left. What output you are getting? Are you getting this?
Yes.
So you have to apply and you need to determine what output you are getting. So this is what is your exercise. Fine. Any doubts with this now? So with this, our chapter is over. From next time, we'll be starting up with a new chapter. So today, actually, we stop here.
Sir.
Yes, yes.
Yeah. सर्कुलर सर्कुलर में
Sorry.
सर्कुलर शिफ्ट राइट लिखा था
हाँ हाँ
उसमें थोड़ा कंफ्यूजन
सर्कुलर शिफ्ट राइट में एक मिनट हाँ एक मिनट yes are you able to see my screen
yes
okay so अभी आप किसमें डाउट है यहाँ पे डाउट है okay yes where the doubt is actually circular shift right okay circular shift right okay so this is my circular shift this is left okay and this is my circular shift right can you see this shifting bit by one position
okay याद आ गया
okay
okay
is it fine
yes
okay so today we stop here any other doubts from anyone else
no
okay so let me take the attendance okay so roll number 109 absent 180
Present.
222
Present, sir.
41
Present, sir.
68
Present, sir.
69
Present, sir.
70 Dwarkesh 71
Yes, sir.
73
Yes, sir.
74
Yes, sir.
75
Yes, sir.
76
Present, sir.
77
Yes, sir.
78 78 78 absent 79
Present, sir.
80 80 absent 81 81 81 absent 82
Present, sir.
83
Present, sir.
84
Present, sir.
85
Present, sir.
86
Present, sir.
87
Yes, sir.
88
Present, sir.
89
Present, sir.
90
Present, sir.
91
Yes, sir.
92 92 absent 93 93 94 sorry 95
Present, sir.
99
Yes, sir.
100
Present, sir.
101
Present, sir.
102
Present, sir.
105
Present, sir.
106 106 absent 108
Present, sir.
109 109 absent 111
Present, sir.
112 112 112 absent. 130,
Present, sir.
133,
Present, sir.
150, 150,
Present, sir.
155.
Present, sir.
D2D series 1,
Present, sir.
2, 2, 2 absent. 3,
Present, sir.
1, 0.
Present, sir.
Okay, just a minute. 4,
Present, sir.
5,
Present.
6, 6 absent. 7,
Present.
8,
Present.
9,
Present, sir.
10,
Present, sir.
11, 11, 11 absent. 12,
Present, sir.
13, 13, 13 absent. 14,
Present, sir.
15,
Yes, sir.
16,
Present, sir.
17, 17,
उसने मैसेज किया है
Present,
उसने।
sir.
17 कौन है?
जीत।
Present, sir.
Okay, 18,
प्रेजेंट सर।
19,
Present, sir.
20,
Present, sir.
21,
21%, sir.
22,
Present, sir.
24,
Present, sir.
25, 25 absent. 26, sorry, 41,
Present, sir.
42, 42 absent. 44, 44,
Present, sir.
45,
Present, sir.
46,
Present, sir.
47,
Present, sir.
48,
प्रेजेंट सर।
49, 49 absent. 50, 50, 50 absent. Okay. Anyone left out for attendance?
Sir, 106.
One by one, one by one. 106. Who is 106? Okay.
Sir, Harsh.
Okay. Next.
सर 42 उसका माइक खराब है।
42.
हाँ
कौन सा 42 कौन सा D2D में?
हाँ
उसका माइक खराब है. ओके
हाँ।
फाइन चलो नेक्स्ट. ओके फाइन.